That'll be fun. All right, well, sometimes it's quote-unquote easy to find whatever the u should be. Because if you have a beefy expression with a radical, odds are it's whatever's under the radical. But sometimes you have a radical that's associated with a question that has an asterisk next to it. So you know something funky's going on with that one. Right? The idea is whatever you call your u should differentiate in such a way that it helps you cancel out everything else that you're not calling u. Right? So in the case of the first one, 200% for those keeping score at home. Did I hit record? I did. I'm going to let u be x squared minus 8x plus 1. Now this is a thoughtless shot in the dark. Okay? And that's sometimes what happens. Like you have a suspicion, so you act on it. So I'm going to take the derivative, du, would be equal to 2x minus 8 dx. All right? This is where you kind of take stock of the situation. Do I have what I need? All right? Well, I have 2x minus 8. That's the same as 2 times x minus 4 in parentheses. All right, well, I have an x minus 4 there, and a dx. I have an x minus 4 and a dx. All right, so I'm double what I want to be. So let me get rid of that 2. So 1/2 du is equal to x minus 4 dx. All right, so now I'm at the point where I can do my substitution. I'm going to replace the highlighted stuff. Let's get it started over here. With a 1/2 du. You can put the 1/2 wherever you want. On the bottom, I'm designating x squared minus 8x plus 1 as my u, so it's now the square root of u. All right, this is really more of an intermediate step than anything else, because you're not going to want to take the antiderivative of that expression the way it is. You want to clean it up first. All right, so this is the same. Oh, I didn't turn on the marker. Same as the antiderivative of 1/2 u to the negative 1/2 du. And again, you know you've selected the correct u if every trace of x is canceled away. Notice how the 1/2 is there, so that's fine. Constant multiples are never a problem. It's the variable x. If I'm substituting, if I'm doing a U-Substitution, x has to go. You can't integrate with both a u and an x in the expression, right, in the integrand. So increase the exponent by 1, divide by the new exponent, you actually just get a clean u to the 1/2 plus c, which is the same as saying x squared minus 8x plus 1 to the 1/2 plus c. Number 7 we can't do yet. I think I mentioned last class that would be a hard one that you should try, but I'm looking at it now. That requires you to take the antiderivative of a tangent function, which requires integration by parts. No, actually, no, it's still doable. No, I was thinking of something else. 8 is the one that looks like it's not something we can do, but it's actually a clever substitution that we can do. 6 is an interesting one. All right, so the thing that's making this funky is the 2x. So normally I do a little baby u-sub, a little u-sub on the fly, but this time I'm going to explicitly state what the u would be, do everything out, because the challenge in this particular problem is not the 2x, it's the secant. It's that we don't know how to take the antiderivative of secant yet, but we're going to learn, and it's going to be glorious. All right, so du would be equal to 2 dx. All right, so I can rewrite, it would be secant of u. The dx is the only thing that I can really get rid of, and in order to do that, I need to divide my differential equation, or my differential form, by 2. So 1/2 du would be equal to dx. All right, so instead of the dx, I'm going to pop in a 1/2 du. That 1/2 is a constant multiplier, so let me take it out of the whole thing. I don't want it in the way, because what I'm about to do, I don't want any distractions to the actual antiderivative of secant. Right? That 1/2, we'll worry about it later. All right. So, antiderivative of secant. If this is something that you would have thought to do on your own, congratulations, you're smarter than me. When I went to find the antiderivative of secant for the first time, I stared at the problem for like, I mean, probably hours, just not all in one stretch. Like 5 minutes, pondered, went away, had lunch, came back, another 5 minutes, pondered again, like, oh, no. I tried things like changing it to 1 over cosine. That didn't help. I tried things like creating a triangle and going right back to basics, SOHCAHTOA, and seeing if I can come up with an algebraic expression. That didn't work. A lot of things didn't work. What did end up working is multiplying it by secant u plus tangent u over secant u plus tangent u. That's what I was talking about before when I said if this is something that you'd come up with on your own, yeah, you're definitely the smarter person, because that if that looks like you just pulled that out of somewhere, then that's right. That is absolutely right. So I always like to think I'm smart enough to understand how it works once I see it, but not always smart enough to actually see where it would come from to begin with. The reason why this is a substitution that's used, not even a substitution, an operation, it's because when I distribute the secant, I get expressions that are anti-differentiable. Secant squared u plus secant u tangent u over secant u plus tangent u du. All right.
So you cancel, you leave only secant squared u?
Well, we don't want to cancel, because if we canceled, then we'd have a problem. We basically go back to where we started. What we actually want to do is take the antiderivative of this now. It's like, whoa, what the hell? Pretty cool, though. I'm going to let u, well, I already got a u, so let me create a new variable. Let's call it v. I'm going to use kind of. So let me just detail it out. I'm going to create a v, a variable v. If you have to do U-substitution twice, you don't want to use u 2 separate times. It'll get confusing. So you could either use subscripts, or you could just work with the next letter in the alphabet. So I think v comes after u. Hopefully it does. Otherwise I've been living a lie. So secant u plus tangent u I'm going to let that be my v, my quote-unquote v. And then I'm going to take the derivative of this. The derivative of secant u, secant u tangent u. The derivative of tangent u, secant squared u. And then I just need the u. So let me just shrink this down a little bit. Squeeze it in. I don't think I wanted that. I just want the v for crying out loud. Alright, whatever. Let's take it all. I guess I got it. Oh. Son of a gun. Get in there. I just need to be able to tuck the du at the end. Let's do it like that. Alright, so now if I take that and compare it to what I have in my actual integral, I have secant u tangent u, I have secant u tangent u, I have a secant squared u, I have a secant squared u, I have an addition sign. Alright, so this would be a direct substitution. So the entire numerator along with the du gets replaced with the dv. Might as well highlight this too. And the bottom is just a u. So we're looking at 1/2. Ooh, that's bold. Too bold. 1/2. We would have dv replacing the top, a u on the bottom. So also I could look at that as 1/u dv. What is the antiderivative of 1/u? ln. ln of u. I got the 1/2 as my coefficient. I'll chuck a plus c on at the end. Alright. Sorry. I wrote u's. Those should have been v's. And now there's no way around it. I just gotta redo it. So it's yeah, it's 1/v dv. Oh wait, no. I'm just trying to make it look like I had it before. It was dv/v. Now it's 1/v dv. dv/v, yeah. Right, because we called secant u plus tangent u to v. Alright, so 1/2 ln of I almost said it again, of v is our antiderivative. So now I can start the process of reverse substituting. So in this case, I'd be looking at a final answer of 1/2 ln secant of the u, but the u is 2x, plus tangent of 2x, plus c. That's awful. All that being said, secant is one of our 6 basic trig functions, and I had mentioned a while ago that those are facts. Like the derivative of sine is cosine, so the antiderivative of cosine is sine. Derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. These are all things that you can assume because they are facts that we use over and over again. So either you can commit it to memory or it can end up on an index card, but you're more than welcome to use the fact that the antiderivative of secant is the natural log of secant plus tangent. Right? So you would not necessarily have to go through this entire process. I just personally don't like the idea that a person can use a tool without knowing how it works. Okay, so I mean, it's not a full-blown proof, but it's at least a demonstration, and that's got some value too. Page width. Oh, you see, I gave you a perfect amount of room. You fit it all in there. Not a problem whatsoever. You know what's going to happen? I'm going to revise everything to the point where you'll have or students will have the perfect amount of room for every question. And then the next day, everything will go digital. And all the students will be able to shrink and expand and stuff like that. And it'll be a complete waste of time. I know, it's just how it goes. It's just no life. All right, so number 7. Initial thought would hopefully revolve around the 4x squared. That's my u. So du would be 8x dx. That's wonderful news, especially after the last problem. Because that's telling me that I can swap out the 8x and the dx for a du. So I'll have a tangent of u du. And that's also something that could be considered fact-based, because it's a tangent function. It's not tangent of the natural log of something else. It's just a tangent function. So if you happen to know what the antiderivative of the tangent function is, you can just jump right to it. I'm going to assume that we don't all know it and act accordingly. So let's redefine tangent as the ratio of sine to cosine. All right. With trig functions involving sine and cosine, there's a U-substitution naturally involved. It's just a question of which one you want to let be the U and which one you want to let be the other thing. In this case, we're going to introduce a V again because I already have a U. So I'm going to let V be the denominator cosine of U. I chose the denominator because that's the thing that's making this difficult. If it would just if this integral was just the numerator, I wouldn't have a problem whatsoever. But because the denominator is there, I get a problem. Now, just kind of imagine this. If I had designated, let's say, the sine of u as my v, and because of that, I ended up with something complicated on the bottom. It might be in terms of v. It still didn't make my integral any easier. It might not be worth it. And it also might paint you into a corner, which is something you don't necessarily want either. You definitely don't want. So differentiate dv is equal to negative sine u du. That's the exact opposite of what I want, so let me negate. Negative dv is equal to the sine of u du. So I can replace the sine of u du with a negative dv. So I'd be looking at negative dv over v, which is the same as negative the integral 1 over v dv. Some kind of recurring theme appears to be at work here. So that's negative the natural log of v plus c, with the v being cosine u, and the u being 4x squared. You could also say of secant too. So you decide well, determine that you need a v once you identified your u, performed all your substitutions, but it didn't really help. We got to a point where you still can't just use a simple rule to come up with the antiderivative, in which case you start thinking, I might need to use substitution again. If that's the case, then you know that it can't be u, so it has to be a v. At that point, you decide it really is a matter of experience in a lot of cases, but generally, when you're dealing with a fraction, the more complicated part of the fraction is the denominator. So wherever possible, I want to get rid of that. Okay. ln of secant? Yeah, because if I use the power rule for logs, this would become a reciprocal function, which would then become secant. So it's equivalent. Negative ln of cosine or ln of secant mean the same thing. All right, so the next one, let me just do this. I want to dedicate a little space to this one. It's kind of crazy because you look at numbers. Well, number 9 isn't difficult at all. Number 10 looks like it would be like astonishingly difficult, but it's not. The one with the asterisk is the crazy one. And the only reason I say that is because it's one of those kind of problems where you could stare at it for a while and not necessarily come up with the right approach. Right? So that's really what the crux of the issue is. All right. So how do we do it? Well, I'm glad you asked. If I'm going to use U-substitution, I need whatever I call U to have a derivative that will cancel out the other part. So I'm gonna do something incorrect first. So feel free not to write it down, but I just want you to see what I'm talking about. So let's say I let U be equal to 16 minus x squared, x to the 6th power. When I go through the process of taking the derivative, I get du equals negative 6x to the 5th dx, which is a big problem because I need to be able to cancel out an x squared dx. Now I can manipulate this expression so that it says x squared. I mean, that's easy enough. I'll just divide by negative 6x cubed, and that'll make an x squared dx. The problem is I'd have this whole expression here that's in terms of a u and an x. That's not good. Right? That means that through the cancellation process, I'm not going to be able to get rid of all of the x's. So something else needs to happen. So what we can do, you can handle this one of two ways. Either way, you're going to get to the right substitution, but it's a clever alternative approach. Sometimes we use a u squared substitution. Right? So I'm going to let u squared be equal to 16. Well, actually, I just want to think this through because I think I can do it with the entire expression, 16 minus x to the 6. Just want to make sure I'm not lying. No, because then I have to. I kind of want to do it. I want to go for it, but I'm not really sure. No, I'll go with what works. I'm going to let u squared be equal to just the x to the 6th. Alright. Alright, then I take the square root. U would be equal to x to the 3rd. Alright. That's the same as saying, so let me rewrite this. That we have 16 minus, instead of x to the 6th, we have x cubed squared. All right. The rationale behind that, now what I wrote in black would be, if you can jump right to that, that's a lot of intuition at work. Whereas this is more procedural, but the idea is that I can't take a meaningful derivative of the x to the 6th power, but I can if it's x to the 3rd power, because x to the 3rd power has a derivative of 3x squared, which is what I'm looking to cancel out. So that would be great news. The issue is, well, how do you get to that without knowing it? And unfortunately, that word experience is going to keep coming back over and over again. Right? So if it means doing my extra practice or going to the OpenStax textbook, going to YouTube, going to specifically on YouTube, Patrick JMT, who I think is a really wonderful resource. I'll make a note of that. If you can't get me, you can always get him. I mean, he won't answer your questions, but you know. I mean, he'll answer. I mean, he may answer your questions, just not intentionally. All right. So you can go to his website, and the lessons are listed by topic. So if you need practice with this, you can get it there. It's really more just video recordings of tutorials. The JMT stands for Just Math Tutoring. So, you know, I don't know the guy, but so I'm not getting any like royalties from this or anything. But I know that that it's good stuff. So it's definitely worth checking out. Better than anything I put together, I'll tell you that. So either way, you can get to this. So we can do our substitution now. I have u, which means, which is x cubed, which means that the du would be 3x squared dx. All right, so that's 3 times more than I need. So let me adjust. 1/3 du equals x squared dx. All right, so there's my substitution. Now I'm looking at 1/3 du over the square root of 16 minus u squared. All right, and I can clean that up in a sec. The sec was me taking a sip of water. So 1/3 antiderivative 1 over the square root of 16 minus u squared du. So we want to try to do something with this. So what we're looking at is something that seems to follow the arc sine derivative rule. So we have 1 over 1 minus u squared times u prime. All right, that would be the derivative if I was looking for the arc sine of u. The issue is I'm looking for the antiderivative. Right, so I can either invent it for you right now, or I might have it in here somewhere, in which case I just copy and paste it. Let me look for it real quick. Where when we get to this step here, you're like, oh wow, that's crazy. Because in theory, all of these were on that formula sheet on page 2 of this packet, or the second page of this packet. And so when I told you to look over those formulas last time, it was with the idea that the payoff would be for a question like this. When you get to this step, like, that's clearly the inverse sine. The problem is I'm a schmuck who didn't have the formulas in there. And so I'm wondering why there wasn't that oohing and ahhing going on. And I almost always know the source. It's usually my fault. And so here we are. All right, so these are rules that should have been on that page and for some reason aren't. All right, so now, hopefully, like you're looking at this model and comparing it to what we have here. A squared minus x squared.
So it would be 4 squared?
It would be 4 squared, yeah. So this is the same as saying 4 squared minus u squared. Right, so I know what the a value is. A is equal to 4. I know what the quote-unquote x value is. That's going to be u. And so now I know what the antiderivative is. 1/3, because there was a constant multiple, it's going to follow this model. So inverse sine of x, the x value, which is u, over the a value, which is 4, plus c, and then I just have to swap out the u for what it really is, in this case x cubed. So 1/3 inverse sine x cubed over 4 plus c. Because there is another way to do it. It's along the lines of what I did before with the antiderivative of secant, where it would have been another one of those. I go through the whole process of U-Substitution followed by p33, and at the very end I say, oh, or you could have just used the formula, and then you get pissed off at me. The first time you let it go, the second time it's like, listen, enough of this. So that was the idea there. But the big challenge in this particular situation is knowing that it doesn't necessarily have to be a u. Maybe you're going to let radical u be equal to something. Eventually, you have to get to a u. You have to do the manipulation, though, in some cases to get there. All right. So yeah, it is like little twists and turns along this U-substitution stuff that make it, in some cases really, really challenging, and in other cases it's not bad at all. All right. The next question, which I'm just going to hop back to, so sorry. I wonder. I don't think there's any chance in hell that I can get this to fit in, but I'm going to try. Oh yeah, plenty of room. There we go. It's like super tiny though. Yeah, but like number 9, like I said, denominator of fraction is often a good choice. So let be equal to your u. X cubed plus 1. du would be 3x squared dx. That's 3 times more than I want. So 1/3 du is equal to x squared dx. All right, so we're looking at 1/3 du over u, which is the same as 1/3 the integral of 1 over u du. And before this class, this particular class, if you didn't know what the antiderivative was of 1 over u, hopefully at the end of this class you do. Making sure that I still have that on. So 1/3, in this case 1/3, times the natural log of u plus c, where the u is equal to x cubed plus 1. The only time you don't need the absolutes for a natural log is if the expression would be non-negative for all x, no matter what anyway. So if I had something like x squared plus 1, sum of squares are always positive. So if that's the case, I wouldn't need the absolutes. But because x could be, like if x is, let's say, -5, this whole expression would be negative. And so I would need the absolute in order for that to play out. Right? Assuming that's even part of the domain to begin with. So the moral of the story, put the absolutes no matter what, and you don't have to worry about it. All right. Number 10, the most intimidating looking one, but one of the easiest ones. So one of the strategies was to take whatever is contained within the denominator and make that your u. So let's try. Take the derivative the derivative of 1 is 0, it's constant, but the derivative of your exponential e, and we'll take some time and really formally discuss things like log and exponential derivative and antiderivatives, and also the inverse trig stuff. It's not going to be like a problem here and a problem there, and you figure out the rest on your own. We'll formally discuss it, but this is something that you should have some experience with. When you're taking the derivative of exponential e, it's exponential e, so rewrite the derivative, or rewrite the original function as part of the derivative. I'm just going to give a little bit more room. E to the negative 4/5 x multiplied by the derivative of the exponent. So the derivative of the exponent is negative 4/5. And then I got to squeeze a dx in there. Just do it like this. All right. So I'm looking at what I have here and what I need. Inventory control. So I need an e to the negative 4/5 x. I have that. So that's this guy. I need a negative 4/5. I got that. I need a dx. Got that. The only thing I'm off by is a negative 1. All right. So I can correct this by negating both sides. So negative du would be equal to this stuff. So negative e to the negative 4/5 x. But then you kind of see it as hopefully a little bit of a waste of time, because that negative 1 is a constant multiple anyway. You don't really need to address it. And besides, by doing this correction here, I'm replacing the entire numerator with a negative du. So it's basically like I'm leaving that negative 1 alone anyway. But either way is fine. It's all going to work out. So I'm looking at negative du over u squared, which is the same as negative u to the negative second du, which anti-differentiates to u to the negative first plus c. And then u is that monstrous expression. And that's all she wrote. All right, so if you identify the appropriate u, everything else works itself out. Pretty easy after that. All right. Easy for a U-substitution question. I want to be completely transparent here. When I was a student, I did not find U-substitution to be easy. All right, and it's mostly because of all this stuff that I'm highlighting, where when I talk about inventory, what do I have, what do I need, that's where I would get lost. And so I don't want to assume that that's necessarily the same for you, but if you're getting jammed up, it's probably not in the idea of choosing a U. It's verifying that that U makes sense in the situation, right? In something like number 12, I mean, we got some easy ones, we got some hard ones. At a minimum, you should get to a point where you recognize that the thing under the radical is probably going to be your U. So if you remember, we set this up as a differential equation just to get it into differential form in order to write it as an integral. So that derivative equation corresponds to this equation. F of x is equal to the antiderivative of all that mess. If I let u be equal to the 8 minus x squared, du would be equal to negative 2x dx, which is precisely what I need. Okay, so I have a negative 2x, I have a negative 2x, I have a dx, I have a dx. So this is a direct substitution. So I'm looking at radical u du which is u to the 1/2, and then integrate. So 2/3 u to the 3/2 plus c. All right. The u itself is equal to the 8 minus x squared. So 2/3 times 8 minus x squared plus c. The only way this differs from what we were working on is that I now need to find the plus c. I screwed up. I lost the exponent, thanks. So f of 2 equals 7. They gave us a condition. They gave us a convenient condition, I think. F of 2 would be 2/3 times 8 minus 2 squared to the 3/2 plus c. And that should be equal to 7 when all is said and done. All right. 8 minus 2 squared, so 8 minus 4 is 4. Raised to the 3/2 power is 8. So 16/3 plus c is equal to 7. 7 is the same as 21/3, so subtract off a 16/3 and you're looking at c is equal to 5/3. So my particular solution, f of x, would be equal to 2/3 8 minus x squared to the 3/2 plus 5/3. Barring any catastrophic calculation error.